So we're going to move up to the next time scale, which is obviously the active break periods. We have already mentioned it in several ways. It's written as a section on intense fine-scale precipitation events, tropical mid-latitude interactions in this paper by Deepti, Subimal, Roxy, and so on. So this is showing mid-latitude tropical interactions, synoptic maps showing the 700 hectopascal precipitable water anomalies in millimeters and mean 700 hectopascal winds in meter per second during the Uttarakhand flooding disaster in 2013, which was a very anomalous event, and we saw that it caused many thousand deaths. This is shown for 13th June, 15th June, and 17th June, and in the lower panels it's the same as in A to C, but for synoptic maps of 850 hectopascal height anomalies and mean 850 hectopascal winds in meter per second. And the main point being made here is that if you look at the precipitable water anomalies, there are intrusions from the mid-latitude on each of these events, or on each of these days, which are considered critical for creating these tropical, extratropical interactions which can drive such very heavy rates of fine-scale precipitation. Is this a typology that applies for a lot of events? Well, mid-latitude interactions are very common during the monsoon season, especially because sometimes the monsoon trough, which should go all the way up to the Himalayan foothills by mid-July or so, doesn't always do that, and if it gets stuck somewhere in the middle, then often there seems to be more favorable conditions for these mid-latitude intrusions, but these are not, I would say, very well understood. But you can clearly see this heavy cyclonic circulation in each case, very intense system here, Uttarakhand being somewhere here, and you can see that system is getting bigger and the interaction continues here, and the system has now still remained cyclonic and has changed its orientation and so on. On lower levels you can see the negative anomalies in 850 hectopascal height, so basically the boundary layer height you can think of as being lower. Low pressure system is very firmly in place corresponding to these precipitable water centers, and the shapes are similar with this cyclonic circulation. So the low latitude jet obviously goes up pretty high and nearly barotropic from the surface up to a few kilometers. The conditions that are typically conducive to this kind of intense fine-scale rainfall in the mountain range especially. First, central to the occurrence of these events is the presence of low-pressure systems in either the Bay of Bengal or the Arabian Sea that carries moisture into the region at lower atmospheric levels. We have that here. You can clearly see that. Second, large-scale forcing from the equatorward extrusion of mid-latitude troughs in the mid to upper troposphere, which also exists, associated with wave breaking downstream of the blocking over western Eurasia, and ridging over the Tibetan plateau is required to orient the moisture flow towards the Himalayas. So you have these ridging and the intrusion from the mid-latitudes related to the Western Asian blocking pattern that is mentioned here. Third, convection triggered by orographic lifting associated with the steep Himalayan terrain forces condensation of this moisture, consequently causes these intense fine-scale precipitation. Again, there are many other processes involved, and not all three are involved all the time, but in 2021, for example, there have been multiple cloud bursts actually starting in May in the pre-monsoon season, going on into July as well. So these have to be understood, especially in terms of how the Arabian Sea low, the dust loading over the northwestern Arabian Sea, is modulating the low-level jet, driving flow into the Himalayan foothills, where cloudbursts tend to become very common with favorable conditions of warm air, heavy supply of moisture, and so on. Right? Looking at the active break periods now in the context of this mid-latitude intrusion, this is another example from this recent paper that just came out. Here, instead of extreme precipitation events, we are going in the other direction and looking at what drives non-El Nino droughts. This could also give us an indication of what drives the non-El Nino floods that we talked about. The blue histogram lines here are the non-El Nino droughts. The red lines are the El Nino droughts. And this paper basically argues by using correlations, for example, of the monsoon droughts with SST patterns. El Nino droughts obviously produce this pattern of typical El Nino forcing with the cold anomalies and the horseshoe pattern on this side, the Western Arabian Sea warming here, which is argued to be also contributing to the warming over the Western Arabian Sea, which is more rapid than the rest of the Indian Ocean. I mentioned that because we will see that in a minute. Plus, there have been decades with more El Ninos during the 80s and 90s, which may have contributed to this kind of warming pattern that we'll come back to later on. But coming back to the droughts, if you look at non-El Nino droughts, you get this no activity here in the tropical Pacific El Nino region, but you get this pattern here in the North Atlantic. And this paper argues that the intrusion, mid-latitude intrusion for creating these non-El Nino droughts is coming from here as Rossby waves into the monsoon region. So it's clear that there are interactions of the mid-latitude with the monsoon processes during the summer months, and it is also related to the intrusion of the PV substance that comes through the westerly duct and the tropical upper tropospheric trough that exists in this region and in this region. That's also related to the easterly jet that goes all the way across over to the West African region and so on. So there are fundamental processes that are related to climatological seasonal conditions, but then you have interannual variability on top, like El Nino or the mid-latitude wave dynamics, which can create intense rainfall anomalies here, which we are looking at droughts, but similar things are possible during the wet years as well. So to add a little bit to that, if you look at the standard deviation of the active break period or intraseasonal timescale precipitation, you can see that there is a maximum here and there is a maximum here, or the Bay of Bengal, and there is generally a maximum in the core monsoon zone, and there is a maximum here or the maritime continent, a maritime ITCZ, and we have of course the mesos coming this way, monsoon depressions going that way, but during the active and break periods we have precipitation here and here oscillating between them on 20 to 60 days, or even 10 to 60 days, or 10 to 90 days, and so on. This is the same thing for interannual timescales. Again, you can see the variability over the ITCZ and the core monsoon zone, Bay of Bengal, Western Ghats, and so on. And there are some debates about whether these are somewhat similar to each other and whether that means interannual variability of the monsoon is related to the intraseasonal variance and so on and so forth. There are opposing sides on that issue, but the main point I want to make is that the warming we see here, this is the trend in sea surface temperature for 62 years. So departures from the global mean SST, not local SST, and era surface winds. So we always want to see thermodynamic and dynamic responses. Winds give you the circulation changes. This is for June to September, and these are for remaining calendar months. And this is the warming pattern that I mentioned before. If you look at the annual mean as well, you'll get a slightly higher warming on the Western Arabian Sea side, which may be contributed to by the El Nino pattern as we saw before. So those are the warming rates there. We will come back to that in terms of the trends in the mean monsoon and supply of moisture we mentioned before, in terms of widespread floods over India being getting most of their moisture from the Arabian Sea and so on. So the point again is that how these warmings affect the marine ITCZ, the circulation, the mesos, which are slowing down in a warming situation, how they affect the monsoon depressions or the frequency of them, synoptic versus low frequency, how that affects the intense rainfall events over core monsoon zone and in the Himalayan regions and so on, are still very much open questions. But in the meantime, the analysis of the active and break periods by Sadanand Pai and colleagues shows that for 1901 to 2013, the low frequency so interannual variation and trends in the active days are looked at here, and there is maybe a decadal pattern to it. There is some trend here and there is a flatter trend here, but overall if you look at the long term, there is a slight trend as well. And then this can be split into shorter active periods of 6 days or so, longer active periods, and then the shorter ones have become more frequent, more intense, which is consistent with the extreme events that we have been talking about. And the break days show the opposite trend here, so downward trend here and a flat trend here, with the overall slightly downward trend over this whole period. In other words, active break periods are intrinsic timescales, but within that we might squeeze out timescales statistically, saying they're getting more intense active over 6 days, but we don't have any fundamental understanding, especially in terms of the mean precipitation change versus extreme precipitation changes. But the duration of break periods have become more frequent somewhat, or frequency of break periods have become more intense, but their intensity is reduced in the sense because of warming and moisture loading. There are more rainfall events within the break periods, so the mean rainfall and even the extremes within the break periods are a little bit higher, but all the activity is in the active periods. So active periods may be getting shorter, more intense, break periods getting more frequent and less intense, okay, in the sense of lack of rainfall or dryness during the break periods. So this is the story of intense rainfalls at fine scales that I combined the general Uttarakhand flood with mid-latitude interactions with how the active break periods are changing and how extremes themselves are getting manifest in the active period, with some change in the character of the active periods, maybe the shorter ones becoming more frequent, but overall there is no real significant trend in the active period or the break period. So unfortunately we have to just say diagnostically what we are observing in the data, and then try to say how these may be able to help us constrain the future projections of extreme events. So we have to extract local scale, daily time scale, intense fine scale, orographic, and so on, and then we still have the aerosol impacts and urbanization impacts left to discuss. Okay, so just remember that extreme events are increasing, they're becoming more widespread, but the exact nature or the processes involved are not always very obvious, and the data is not enough, and process understandings are not complete yet, but models are doing better, so hopefully better understanding will evolve from the models themselves as well.